So previously we have derived some sort of a weak form equation with a very simple and really no meaning weak form. Alright, we stop here already, right? Now we're going to derive the Galerkin's method, alright, using our weak form, because this form is just some general stuff, because we actually didn't tell you that what is the function. We call this W the weighting function. Can be any function, right? So therefore in our case we'll sub in W as our shape function, meaning later on we'll talk about it. Alright, now I'll just inform you that W will eventually becomes shape function n1 and n2. Later on we'll go in, when we go into details, I'll start to elaborate what is these things. But so you just take note that this is n1 first. Alright, so this shape function tells you the shape of the system. Alright, someone tells the shape of the system, and b1 is equals to your derivation of your shape across your dx. So for example, you have this bar over here, or you have a certain shape. Maybe when you have a certain shape, like maybe this is your bar, this is the shape. Alright, when you differentiate across a certain dx, alright, you're talking about changing the shape already, somewhat changing the shape. So you may change upwards like this, or you may change with a certain strain, or whatever thing it is. Alright, and therefore this B1 we call this the strain displacement matrix, because it tells you how does the shape change due to dx. Alright, and this shape change is due to certain strain that is within it, within the system, because you're gonna change, right? Because eventually your original length is like this, you may actually change in this manner. So you have certain small changes of length divided by your L will have certain strain, you would say. You may also change in this shape over here. Alright, things like that. And just to take note that this strain displacement matrix tells you that you're actually changing the shape to some extent. Alright, and nonetheless, I'm going to still talk to you that Galerkin's method will sub in the shape function as your weight function, W. So for this case, therefore, now my W over here, I'll sub it as N1. My W over here, I'll sub it as N1 over here. While the rest are the same. I didn't cheat your feeling. Okay, you can double check. The U, the X, everything are all the same. Okay, yeah, I didn't cheat your feeling. They're all the same. Okay, so next step, let's continue. Now I'm gonna sub in this one over here. Since we know that this is equals to this, and it's also equals to this, your strain displacement matrix telling you the changes of the shape across dx. So I'll just sub in as b1. Okay, because I sub in as w as equals to n1. You can sub in as w equals to n2. For our case, I just sub it as n1 will do. Because I'm looking in terms of the node 1. Alright, later on you get what I mean. Alright, maybe you have a bar over here, and then you set it as node 1, you set it as node 2, something. So we're talking about node 1 only. How does the system change across at node 1? Alright, maybe you may actually change shape like this, things like that. Later on I'll go into that. Alright, keep later on. But anyway, and then since we have proved to you that this is equals to this already, the next thing that is I'm going to multiply a times dx. So therefore I have dv over here. While the e is the same over here, du dx, I didn't change, I leave it here. Alright, this whole thing over here, I didn't cheat your feeling, I didn't change anything at all. You can double check the ball. Okay, so I didn't cheat your feeling. The next step is to simply expand this dude, because it's some definite integral. And therefore when I sub in 2 into this equation, alright, I don't know what's into dx, I would think, I don't know which one, but anyway, you have this thing over here, minus away when you sub in 1 into this equation. Alright, so there's something here. So you just simply expand this thing into here, that's all. Okay? And therefore at this point of time, we can introduce our shape function, n1. Okay? So for example, you have a certain bar over here. Alright? If you have to extend it, maybe I should draw it in a straight line. Okay, I have a 1, I have a 2. This is node 1 and node 2. Okay? And then I have this shape over here, I call this n1. This line over here, I call this n1. Alright? So at n1, node 1, I have somewhat a magnitude of 1 over here. this one over here is somewhat a unique vector. Alright, when you multiply this 1 times u1, for example, some displacement, alright, maybe u1 is maybe 2 or 3 or whatsoever, you will, instead of this shape over here, you will have a steeper shape, like n1. So this thing over here is your u1 times your 1. Alright, so it's at node 1, node 2. So as you can see, the changes in the displacement at node 1 is defined already. Alright, so your u1 is some values. It can be higher, it can be lower, it can be going in this direction also can. Alright, it depends on which u1 you sub in. And therefore the simple shift function, the very primitive one, is the n1. Okay, so if n1 at node 1, you have a 1 over here. Then as you can see, at n1 and node 2, it simply is equals to 0, because we are dealing only in the node 1 direction. Alright, and therefore if you want to talk about node 2, alright, which is this thing over here, alright, then it's different. You're gonna say that you're gonna take note of the changes in the node in the node 2 direction. Alright, you're not gonna talk about the node 1 direction anymore, because node 1 direction is being discussed over here. Alright, so same thing if you were to so this is magnitude of 1. Alright, it's something like a unit vector also. So if you multiply it with your u2, you can actually extend this up to here. Your n2 will be something like this already. Or you can also have a minus u2, such that you'll go in this manner. And this thing over here is also your n2. So it depends on which u2 you sub in already. Same thing as your u1. Okay? And therefore in such of our case, alright, because we are concentrating on node 1, everything we're talking about is all 1, 1, 1. So we are talking about node 1. So at node 1, and at node 1, n1, shape function n1, alright, is 1. Okay? At node 2 is equals to 0. So therefore, at n1, shape function 1, alright, at node 2 is equals to 0, which is as we have said, over here is equals to 0. And then at n1, node 1, which is over here, is equals to 1. It spikes out. Okay, so far so good. And therefore, in such a case that happens, alright, then at n1, because this is at node 2, this is at node 1, alright, and therefore at node 2, we know that it's equals to 0, so this n1 over here is 0. As you can see, at n1 node 2 is equals to 0. So this at this node 2 over here is equals to 0, and therefore this whole thing becomes 0. And therefore I cancel it out. Okay? And then at node 1, I mean at n1 node 1, which is this node 1 over here, or node 1 over here, it is equals to 1. So your n1 over here is equals to 1. Ea du dx. So therefore I have minus, so this is 0. 0 minus Ea du dx is simply minus Ea du dx over here. So I'll just simply bring it all over here now. Okay? So far, so good. Wow, this thing over here, I didn't cheat a feeling, I bring it all the way down. It's the same thing. Although it's very messy right now, but as you can see, b1 is the same as b1 over here. Du dx E is the same thing, dv is also the same thing. Alright, so I'll simply bring all the way all this down. Okay? So let me rearrange something because it's really messy, as you can see now. So now I'll introduce you two things. Alright, I'll just introduce two things now. Alright, that minus Ea du dx is equals to your f1. Alright, minus Ea du dx at node 1 now. Okay, is equals to your first one. And the next thing I'm going to introduce you is that this thing over here is equals to this thing over here. Okay, so I'll just do it a quick one for this one first. If you were to head back, picture over here, if you still remember, this is from your first video. If you want to check it out, you can go to l8v4. This is the first video. We actually discuss things like this. Alright, we said that the F1, because this is internal forces, alright, plus the F1 over here, alright, is equals to 0 because of the equilibrium theory, or equilibrium theory. While F2, because it's going in this direction, minus force internal is going in this direction, therefore is equals to 0. Okay, pretty clear, right? So if I were to have F1 plus F internal is equals to 0, which is this one because they are going in the same direction, then if I were to bring the F internal over to the other side, I have F1 is equals to minus F internal. Okay, And in fact, this thing over here is the F internal equation. Alright, it's EA over L, U2 minus U1. Okay, so K is your EA over L, right? And then, since this is U2 minus U1, this means that this is some form of a change in U. Correct? Or you can call this du. Then because we are now analyzing the element in terms of dx, a very small dx only, and therefore on length over here, instead of L we can say that it's dx, and therefore I have EA du dx. Alright, don't forget the minus, because it's minus sign over here. So therefore I have F1 is equals to minus EA du dx. Okay, so with these things over here, I'll just simply copy this thing and I'll just paste it in front of you, so that at least you know what I mean and I didn't cheat your feeling. Is this. Okay, so I have my minus EA du dx over here. Same thing. So I can simply sub in as equals to F1, your node 1 over here. Okay, so I hope that this is pretty clear. So far so good. Perhaps I should bring this thing, alright, downwards, because it will actually make you feel more intimidated with seeing that matrix. Alright, but it's the same thing, alright, it's the same thing only. This thing over here is the same as equals to F1, while this thing over here, the only difference is that I change U as equals to N1 U1 plus N2 U2. Okay, so if you are to take note, U is equals to N1 U1 plus N2 U2. How does this come from? If you still remember our shape function, this is the N1. If at node 1 you have 1, alright, 1 unit vector. At N2 you will have 1 at the node 2 unit vector. Alright, and you can multiply by how many times U1 is. If you have a U1 that is times 2, then you will have a 2 over here, and then this is N1. So this tells you that your displacement has changed in this manner. Okay, and then if you have a U2 in this case, maybe it's going in this direction. Alright, and we have a minus 2. I have something like this already. Alright, and this is my N2. Then if you were to combine this shape all together, you have something like this. Alright, so we have our N1 U1, and you have a N2 U2. Correct? Because you are at a U1 is 2, right? 2N1, and then at the over here is minus 2. I think you get what I mean? So this shape over here is this shape, or this shape over here that I've just drawn for the N1 function. Where's my pen? Then this shape all over here is this shape. Okay, so you have a different, when you combine N2 and N1 all together, you have all different shape. You can have something like this, as we have drawn just now. You can also have something like this. You can also have something like this. Maybe not something like this, or maybe your N1 may be smaller, your N2 may be higher. You have different shapes. So this tells you that your displacements at node 1 and node 2 is different. And this explains why in your normal meshes in your SolidWorks and things like that, you often see some triangular, some whatever triangular, and this is something like this. I'm talking about that actually. Okay, so therefore this is just the meaning of that. So we can, if you were to merge your overall displacement, because now you are talking about N1, maybe N1 is here, U1 because you have some multiplication, and then we have another N2 shape like this, U2. So if you were to put them together, it's just simply the whole displacement. Alright, at this point, the overall displacement. I don't know how to visually tell you the overall displacement, but at least you can see that at node 1 and node 2 previously was here, but at the end of the day, they actually zoom out into here. Alright, so the overall displacement is N1 U1 plus N2 U2. Okay, and if you take derivative du over dx, then you have a du dx and du dx over here. So as you can see, N1 U1, alright, is this thing over here, multiplied by your d over dx, or your N2 U2 is simply this one over here, d over dx. So therefore your u is simply N1 U1 plus N2 U2, and because of the d over dx multiplication, you're going to multiply both of them together. While the e times dv is the same, we didn't change. b1 we didn't change also. Okay, I hope this is pretty clear, right? At least you have seen other stuff. Okay, and nonetheless we can also write this thing over here as a matrix, because your n1 u1 can be written as a matrix form like this. This is nt, this is your ui. Okay, and therefore you can just simply do it over here, right here, your dot product. Okay, so far so good. Alright, nonetheless I will utilize this form and continue. Alright, I'll go on to this side. So if I were to go on, okay, I have this thing, it's the same thing, I didn't change your filling. Alright, and next step we're gonna do, and if you still remember, we have n1 over dx as the strain displacement matrix b1. Alright, talking about how the change of the geometry is. You have a shape over here, you have a certain strain that occurs or certain displacement that occurs, you may actually change the shape like this. So in the end you have something like this. So it's somewhat the displacement matrices, something like the strain displacement matrix. So you just subplane your dn1 as b1, subplane your dn2 as b2. Okay, so far so good. And therefore you have this form, f1 is equals to this thing. Alright, so therefore this thing over here is to represent your force 1. Okay, so what I've been deriving all along is to first we told you that the Galerkin's method is to sub in your w as a shape function n. Alright, we will sub in your shape function at n, and then also telling us that the changes of n with x with respect to x is the strain displacement, telling you that the shape changes across x. Alright, and then we do a series of rearranging and things like that, and subbing in and here and there. We eventually solve and tell us that we have a force, we can represent the force 1 in terms of this equation over here. Okay, and therefore with doing the same thing for our force 2, you have this thing over here. This is totally the same, it's just doing 2 steps. Alright, so if we let w is equals to n2, as we say just now in the very first part, we let, what do we let? We let w as equals to n1. Alright, so at first my w was this one, right, w. So I set it as n1, and therefore I have n1 and my n1 over here, and I continue to calculate stuff, and eventually I solve for force 1. Now instead I'll just sub in w as n2, and then I'll just continue to solve. Eventually you'll still get to see that we will get back to this form. So this will represent our force 1, and this will represent our force 2. Okay, so in the next video, I think that it will be pretty short. Alright, but we haven't finished the whole series yet, but we will derive only this one, the constitutive equations. So this is in fact our weak form. Alright, the general weak form. Alright, so this is in the next video we'll talk about this, and I shall see you there.